Natural language processing is a field of computer science, artificial intelligence, and computational linguistics concerned with the interactions between computers and human languages. As such, NLP is related to the area of human-computer interaction. Many challenges in NLP involve natural language understanding, that is, enabling computers to derive meaning from human or natural language input, and others involve natural language generation. History. The history of NLP generally starts in the 1950s, although work can be found from earlier periods. In 1950, Alan Turing published an article titled Computing Machinery and Intelligence, which proposed what is now called the Turing Test as a criterion of intelligence. The Georgetown experiment in 1954 involved fully automatic translation of more than 60 Russian sentences into English. The authors claimed that within 3 or 5 years, machine translation would be a solved problem. However, real progress was much slower, and after the ALPAC report in 1966, which found that 10-year-long research had failed to fulfill the expectations, funding for machine translation was dramatically reduced. Little further research in machine translation was conducted until the late 1980s, when the first statistical machine translation systems were developed. Some notably successful NLP systems developed in the 1960s were SHRDLU, a natural language system working in restricted blocks worlds with restricted vocabularies, and ELIZA, a simulation of a Rogerian psychotherapist, written by Joseph Weizenbaum between 1964 to 1966. Using almost no information about human thought or emotion, ELIZA sometimes provided a startlingly human-like interaction. When the patient exceeded the very small knowledge base, ELIZA might provide a generic response, for example, responding to, "My head hurts," with, "Why do you say your head hurts?" During the 1970s, many programmers began to write conceptual ontologies, which structured real-world information into computer-understandable data. Examples are Margie, Sam, Pam, Tailspin, Quam, Politics, and Plot Units. During this time, many chatbots were written including Parry, Racter, and Jabovatsky. Up to the 1980s, most NLP systems were based on complex sets of handwritten rules. Starting in the late 1980s, however, there was a revolution in NLP with the introduction of machine learning algorithms for language processing. This was due to both the steady increase in computational power and the gradual lessening of the dominance of Chomskyan theories of linguistics, whose theoretical underpinnings discouraged the sort of corpus linguistics that underlies the machine learning approach to language processing. Some of the earliest used machine learning algorithms, such as decision trees, produced systems of hard if-then rules similar to existing handwritten rules. However, part of speech tagging introduced the use of hidden Markov models to NLP, and increasingly, research has focused on statistical models, which make soft probabilistic decisions based on attaching real-valued weights to the features making up the input data. The cache language models upon which many speech recognition systems now rely are examples of such statistical models. Such models are generally more robust when given unfamiliar input, especially input that contains errors, and produce more reliable results when integrated into a larger system comprising multiple subtasks. Many of the notable early successes occurred in the field of machine translation, due especially to work at IBM Research, where successively more complicated statistical models were developed. These systems were able to take advantage of existing multilingual textual corpora that had been produced by the Parliament of Canada and the European Union as a result of laws calling for the translation of all governmental proceedings into all official languages of the corresponding systems of government. However, most other systems depended on corpora specifically developed for the tasks implemented by these systems, which was a major limitation variation in the success of these systems. As a result, a great deal of research has gone into methods of more effectively learning from limited amounts of data. Recent research has increasingly focused on unsupervised and semi-supervised learning algorithms. Such algorithms are able to learn from data that has not been hand-annotated with the desired answers, or using a combination of annotated and non-annotated data. Generally, this task is much more difficult than supervised learning, and typically produces less accurate results for a given amount of input data. However, there is an enormous amount of non-annotated data available, which can often make up for the inferior results. NLP using machine learning. Modern NLP algorithms are based on machine learning, especially statistical machine learning. The paradigm of machine learning is different from that of most prior attempts at language processing. Prior implementations of language processing tasks typically involved the direct hand coding of large sets of rules. The machine learning paradigm calls instead for using general learning algorithms, often, although not always, grounded in statistical inference, to automatically learn such rules through the analysis of large corpora of typical real-world examples. A corpus is a set of documents that have been hand-annotated with the correct values to be learned. Many different classes of machine learning algorithms have been applied to NLP tasks. These algorithms take as input a large set of features that are generated from the input data. Some of the earliest used algorithms, such as decision trees, produce systems of hard if-then rules, similar to the systems of handwritten rules that were then common. Increasingly, however, research has focused on statistical models, which make soft, probabilistic decisions based on attaching real-valued weights to each input feature. Such models have the advantage that they can express the relative certainty of many different possible answers rather than only one, producing more reliable results when such a model is included as a component of a larger system. Systems based on machine learning algorithms have many advantages over hand-produced rules. The learning procedures used during machine learning automatically focus on the most common cases, whereas when writing rules by hand it is often not obvious at all where the effort should be directed. Automatic learning procedures can make use of statistical inference algorithms to produce models that are robust to unfamiliar input and to erroneous input. Generally, handling such input gracefully with handwritten rules, or more generally, creating systems of handwritten rules that make soft decisions, is extremely difficult, error-prone and time-consuming. Systems based on automatically learning the rules can be made more accurate simply by supplying more input data. However, systems based on handwritten rules can only be made more accurate by increasing the complexity of the rules, which is a much more difficult task. However, creating more data to input to machine learning systems simply requires a corresponding increase in the number of man-hours worked, generally without significant increases in the complexity of the annotation process. The subfield of NLP devoted to learning approaches is known as natural language learning, and its conference CON and peak body SIGNLL is sponsored by ACL, recognizing also their links with computational linguistics and language acquisition. When the aim of computational language learning research is to understand more about human language acquisition, or psycholinguistics, NLL overlaps into the related field of computational psycholinguistics. Major tasks in NLP. The following is a list of some of the most commonly researched tasks in NLP. Note that some of these tasks have direct real-world applications, while others more commonly serve as subtasks that are used to aid in solving larger tasks. What distinguishes these tasks from other potential and actual NLP tasks is not only the volume of research devoted to them but the fact that for each one there is typically a well-defined problem setting, a standard metric for evaluating the task, standard corpora on which the task can be evaluated, and competitions devoted to the specific task. Automatic summarization produces a readable summary of a chunk of text, often used to provide summaries of text of a known type, such as articles in the financial section of a newspaper. Coreference resolution. Given a sentence or larger chunk of text, determine which words refer to the same objects. Anaphora resolution is a specific example of this task, and is specifically concerned with matching up pronouns with the nouns or names that they refer to. The more general task of coreference resolution also includes identifying so-called bridging relationships, involving referring expressions. For example, in a sentence such as, he entered John's house through the front door. The front door is a referring expression, and the bridging relationship to be identified is the fact that the door being referred to is the front door of John's house. Discourse analysis. This rubric includes a number of related tasks. One task is identifying the discourse structure of connected text, i.e., the nature of the discourse relationships between sentences. Another possible task is recognizing and classifying the speech acts in a chunk of text. Machine translation automatically translate text from one human language to another. This is one of the most difficult problems, and is a member of a class of problems colloquially termed AI complete, i.e., requiring all of the different types of knowledge that humans possess in order to solve properly. Morphological segmentation. Separate words into individual morphemes and identify the class of the morphemes. The difficulty of this task depends greatly on the complexity of the morphology of the language being considered. English has fairly simple morphology, especially inflectional morphology, and thus it is often possible to ignore this task entirely and simply model all possible forms of a word as separate words. In languages such as Turkish or Manipuri, a highly agglutinated Indian language, however, such an approach is not possible, as each dictionary entry has thousands of possible word forms. Named entity recognition. Given a stream of text, determine which items in the text map to proper names, such as people or places, and what the type of each such name is. Note that, although capitalization can aid in recognizing named entities in languages such as English, this information cannot aid in determining the type of named entity, and in any case is often inaccurate or insufficient. For example, the first word of a sentence is also capitalized, and named entities often span several words, only some of which are capitalized. Furthermore, many other languages in non-Western scripts do not have any capitalization at all, and even languages with capitalization may not consistently use it to distinguish names. For example, German capitalizes all nouns, regardless of whether they refer to names, and French and Spanish do not capitalize names that serve as adjectives. Natural language generation. Convert information from computer databases into readable human language. Natural language understanding converts chunks of text into more formal representations such as first-order logic structures that are easier for computer programs to manipulate. Natural language understanding involves the identification of the intended semantic from the multiple possible semantics which can be derived from a natural language expression, which usually takes the form of organized notations of natural languages concepts. Introduction and creation of language metamodel and ontology are efficient, however, empirical solutions. An explicit formalization of natural languages semantics without confusions with implicit assumptions such as closed-world assumption versus open-world assumption, or subjective yes/no versus objective true/false is expected for the construction of a basis of semantics formalization. Optical character recognition. Given an image representing printed text, determine the corresponding text part of speech tagging. Given a sentence, determine the part of speech for each word. Many words, especially common ones, can serve as multiple parts of speech. Some languages have more such ambiguity than others. Languages with little inflectional morphology, such as English, are particularly prone to such ambiguity. Chinese is prone to such ambiguity because it is a tonal language during verbalization. Such inflection is not readily conveyed via the entities employed within the orthography to convey intended meaning. Parsing determine the parse tree of a given sentence. The grammar for natural languages is ambiguous and typical sentences have multiple possible analyses. In fact, perhaps surprisingly, for a typical sentence there may be thousands of potential parsers. Question answering given a human language question, determine its answer. Typical questions have a specific right answer, but sometimes open-ended questions are also considered. Recent works have looked at even more complex questions. Relationship extraction given a chunk of text, identify the relationships among named entities. Sentence breaking given a chunk of text, find the sentence boundaries. Sentence boundaries are often marked by periods or other punctuation marks, but these same characters can serve other purposes. Sentiment analysis extracts subjective information usually from a set of documents, often using online reviews to determine polarity about specific objects. It is especially useful for identifying trends of public opinion in the social media, for the purpose of marketing. Speech recognition given a sound clip of a person or people speaking, determine the textual representation of the speech. This is the opposite of text-to-speech and is one of the extremely difficult problems colloquially termed AI complete. In natural speech there are hardly any pauses between successive words, and thus speech segmentation is a necessary subtask of speech recognition. Note also that in most spoken languages, the sounds representing successive letters blend into each other in a process termed co-articulation. So the conversion of the analog signal to discrete characters can be a very difficult process. Speech segmentation given a sound clip of a person or people speaking, separate it into words. A subtask of speech recognition and typically grouped with it. Topic segmentation and recognition given a chunk of text, separate it into segments each of which is devoted to a topic, and identify the topic of the segment. Word segmentation separate a chunk of continuous text into separate words. For a language like English, this is fairly trivial, since words are usually separated by spaces. However, some written languages like Chinese, Japanese and Thai do not mark word boundaries in such a fashion, and in those languages text segmentation is a significant task requiring knowledge of the vocabulary and morphology of words in the language. Word sense disambiguation. Many words have more than one meaning. We have to select the meaning which makes the most sense in context. For this problem, we are typically given a list of words and associated word senses, e.g., from a dictionary or from an online resource such as WordNet. In some cases, sets of related tasks are grouped into subfields of NLP that are often considered separately from NLP as a whole. Examples include information retrieval. This is concerned with storing, searching and retrieving information. It is a separate field within computer science, but IR relies on some NLP methods. Some current research and applications seek to bridge the gap between IR and NLP. Information extraction. This is concerned in general with the extraction of semantic information from text. This covers tasks such as named entity recognition, coreference resolution, relationship extraction, etc. Speech processing. This covers speech recognition, text-to-speech and related tasks. Other tasks include native language identification, stemming, text simplification, text-to-speech, text proofing, natural language search, query expansion, automated essay scoring, true casing, statistical NLP. Statistical natural language processing uses stochastic, probabilistic, and statistical methods to resolve some of the difficulties discussed above, especially those which arise because longer sentences are highly ambiguous when processed with realistic grammars, yielding thousands or millions of possible analyses. Methods for disambiguation often involve the use of corpora and Markov models. The Esprit Project P26, led by CSELT, explored the problem of speech recognition comparing knowledge-based approach and statistical ones. The chosen result was a completely statistical model. One among the first models of statistical natural language understanding was introduced in 1991 by Roberto Piracini, est11, and Chin-Hui Lee from Bell Laboratories. The technology for statistical NLP comes mainly from machine learning and data mining, both of which are fields of artificial intelligence that involve learning from data.